All right, welcome to another deep dive. So you know the drill. You guys send in stuff you're curious about, and we take a look. And today we have a really interesting one. Someone sent in a YouTube discussion featuring Oxford's Michael Wooldridge, and it's about AI, obviously. So
Mhm.
we're going to do a deep dive into the history of AI.
It's a fascinating looking back at how we got to where we are. I mean, AI is everywhere now, but most people probably don't know the history, all the twists and turns.
Exactly. And for our listener out there who wants to really grasp AI and its potential impact, not just the headlines, well, we're going to map out the evolution of this whole field. Like, how did we get from basic calculators to Chat GPT? And what can we learn from that journey to figure out where AI might be going next?
Yeah, the source material really emphasizes that studying AI's past can give us a clearer picture of the present. Like, are we really on the verge of some huge AI revolution, or is this just another help cycle? We've seen those before, right?
Oh, yeah, plenty of times. But there's another reason to dig into AI history. Sometimes really valuable ideas get forgotten or overlooked. I mean, think about, how many scientific discoveries were made by accident or how old philosophies come back into fashion. So yeah, going back in time might help us find new solutions to today's problems.
Absolutely. The source mentions a few key milestones that have brought us to this point: deep learning taking off around 2005, the use of GPUs for neural networks around 2012, the transformer architecture in 2017, and GPT-3 coming out in 2020.
Right, and that shift from painstakingly crafting algorithms where every step was explicitly defined
Yeah.
to this era of data-driven machine learning, that's been huge. Suddenly we have systems that can do things that were thought to be impossible, but we often don't fully understand how they do it.
Exactly. And there's a trade-off there, right? We've lost some of that guarantee of correctness that we had with older methods. But in return, we've gotten systems that can tackle much more complex and nuanced problems, even if they're not always perfect.
Right. And that's exactly what we're seeing with these incredibly impressive large language models, LLMs. They can write poems, translate languages, even generate code, but they also make mistakes, sometimes in hilarious ways. So it's this kind of black box situation. We're still figuring out how to interpret what they're doing and what their limitations are. But before we get ahead of ourselves, let's go back to the very beginning. I mean, before deep learning, before LLMs, there was this whole era of what's known as symbolic AI. And that's where the story really starts with the work of a true legend, Alan Turing.
Turing, now universally recognized as the father of theoretical computer science and AI, was grappling with some pretty profound questions back in the 1930s, even before computers as we know them existed. His doctoral research was focused on something called the Entscheidungsproblem, which is German for decision problem. Essentially, he was trying to figure out if there was a way to automate mathematical reasoning, to create a machine that could, in principle, solve any mathematical problem.
That's mind-blowing to even think about, really. I mean, this is
Yeah.
before computers, before transistors, even before World War II.
Exactly. And in his attempt to tackle this purely theoretical problem, Turing came up with the concept of the Turing machine. Imagine a machine that operates on a strip of tape, reading and writing symbols according to a set of very precise rules. Now, initially, this was just a mathematical abstraction, a thought experiment. But Turing's later work on actual code-breaking machines during the war, as well as the efforts of others to build the first computers, led to the realization that these abstract Turing machines could actually be built.
It's fascinating that the modern computer, in a way, is a byproduct of this very abstract, very theoretical mathematical quest.
Precisely. And what really sparked the whole field of AI was the observation that even these very early primitive computers, which could barely do basic arithmetic by today's standards, were nevertheless exhibiting behavior that seemed surprisingly intelligent. They could perform calculations far faster and more accurately than any human could. And people started to wonder, if machines could excel at this, what else could they do?
It's mind-boggling that within just a few years, we went from having virtually no computers to machines that could perform basic planning, problem solving, and even play games like checkers. And as our expert source emphasizes, the instructions given to these early computers were incredibly rudimentary, just simple step-by-step commands, very unambiguous and explicit.
That's an important point. The foundations of computing, even today, still rely on this basic principle, orchestrating incredibly simple, deterministic instructions to achieve complex outcomes. I mean, when you think about it, it's a pretty remarkable philosophical leap to consider how the complex, seemingly intelligent output of modern AI, like ChatGPT, ultimately emerges from this massive symphony of simple deterministic steps.
Right. It really challenges our intuitions about what intelligence is and where it comes from.
Mhm.
I mean, can something that fundamentally operates on such basic deterministic instructions truly be considered intelligent in the same way that we are? The transcript even mentions the debate about whether determinism can truly give rise to non-deterministic outcomes. It's a pretty deep philosophical question, and one that AI forces us to confront.
And of course, there's also the question of consciousness. We humans are fundamentally embodied beings. We experience the world through our senses. We have emotions. We feel pain and joy. As far as we know, machines don't have those capacities, at least not in the same way that we do. So even if a machine can perform tasks that we consider intelligent, does that necessarily mean it's experiencing the world in a way that's even remotely similar to us?
Absolutely. And that leads us to the other concept that Turing is so well known for, the Turing test. He devised this test in the 1950s, partly out of frustration with all the pronouncements about what computers could never do. People would say computers can never be creative or they can never truly understand anything. And Turing wanted to offer a more concrete way to address these claims.
Yeah, he was really pushing back against those dogmatic assertions. So the Turing test, in its essence, is about indistinguishability. You have a human judge who's interacting with two entities, one human and one machine, through text-based communication. The judge doesn't know which is which, and if they can't reliably tell them apart, if the machine can effectively convince the judge that it's human, then Turing argued that the debate about whether the machine is truly thinking becomes pretty pointless.
So it's not about proving that the machine has consciousness or emotions or anything like that. It's about whether it can produce behavior that is indistinguishable from human behavior.
Hmm.
And there are a couple of ways to interpret this. One is that if something acts intelligent, then for all practical purposes, it is intelligent. The other interpretation is more about, well, if we can't tell the difference, does the question of what's really going on inside the machine even matter?
Right. And our expert source seems to think that Turing was probably more interested in ending the debate than providing a definitive answer to that question. But, it does raise some interesting parallels with behaviorist psychology, which also focused primarily on observable behavior. It makes you wonder if just being able to mimic intelligent behavior is really the same as possessing genuine understanding.
Yeah, exactly. And that distinction is often framed as strong AI versus weak AI. Strong AI would be a machine that genuinely understands and experiences the world in a way that's comparable to humans,
Mm.
whereas weak AI is focused on simply simulating intelligent behavior without necessarily having those deeper capacities. And most AI research today, I think it's fair to say, is aimed at weak AI.
Right. And when you start talking about strong AI, it naturally leads to questions about moral agency for machines. Like, if a machine could genuinely suffer, would we have moral obligations towards it? It's a fascinating area to think about. But the source also warns against the idea of moral AI, suggesting that trying to program morality into machines might just be a way for humans to abdicate their own moral responsibilities for the actions of AI.
Yeah, that's an important point to consider. Ultimately, it's humans who are creating and deploying these technologies, and it's humans who need to be held accountable for their impact. Okay, so we've talked about Turing and his groundbreaking ideas. Now let's move on to the first major boom in AI, often called the Golden Age, which lasted from roughly the mid-1950s to the early 1970s. What was going on during that period?
The Golden Age was all about symbolic AI. The main idea was to try to model the workings of the human mind using explicit symbols and logical rules. Remember, this was a time of great optimism about the potential of computers. We had seen machines doing things that were previously thought to be exclusively human, and people were really excited about the possibilities.
So they were basically trying to figure out how to program intelligence by explicitly representing knowledge and reasoning processes in a symbolic form.
Exactly. The approach was basically identify tasks that require human intelligence and then try to build computer programs that can do those tasks using symbolic manipulation. And there was a lot of early success, which further fueled the optimism. Machines were proving mathematical theorems, solving logical puzzles, even playing chess at a decent level. There were predictions that full-blown human-level AI was just a few decades away.
Sounds familiar, right?
Mm,
AI hype is definitely not a new thing.
not at all. But there was a problem. This early progress started to slow down by the late 1960s, early 1970s. And one of the main reasons was that researchers were focusing on overly simplified versions of real-world problems. They were working in what they called micro-worlds, kind of like simulated environments.
So they might build a program that could, say, navigate a simulated robot through a warehouse, But that success wouldn't necessarily translate to a real robot in a real messy, unpredictable warehouse.
Right. And another issue was that they were mostly relying on search algorithms.
Yeah.
So imagine you're trying to find the best solution to a problem. You have to search through all the possibilities. Well, as the problem gets bigger, the number of possibilities explodes. It becomes computationally impossible to check them all.
Like trying to find a specific grain of sand on a beach.
Yeah, exactly. This is what's known as the combinatorial explosion, and it was a major roadblock for a lot of the problems that AI researchers were trying to tackle. For example, the traveling salesman problem, finding the shortest route that visits a set of cities, gets incredibly difficult very quickly as you add more cities.
Right, the number of possible routes just goes through the roof. So they hit this computational wall, basically.
Yeah. And to make matters worse, in the early 1970s, a new field emerged called computational complexity theory, and it showed that many of the problems AI was trying to solve were fundamentally difficult. They belong to a class called NP-complete, which basically means that there's no known efficient way to solve them. The only guaranteed method is to try out every single possibility, which is practically impossible for any problem of reasonable size.
So the golden age of AI basically ran out of steam because the problems turned out to be much harder than they initially thought.
Exactly. And as the initial optimism faded and those grand predictions failed to materialize, the funding dried up and we entered the first AI winter. It's interesting to note that even relatively recently, before the current deep learning boom, AI had a pretty bad reputation in some scientific circles. Neural networks, in particular, were considered a dead end.
But of course, AI didn't stay dormant forever. In the 1980s, we saw the rise of expert systems. What was the thinking behind those?
Well, expert systems were driven by the idea that intelligence is mostly about knowledge. If you can capture the knowledge of human experts in a specific domain and put it into a computer system, then that system should be able to perform tasks that require that expertise. The key technology was rule-based systems, where you represent knowledge as a set of if-then rules.
So like if you have a fever and a cough, then you might have the flu.
Yeah, exactly. And a famous example from that time was the MYCIN system, which was designed to diagnose blood diseases. They basically interviewed a bunch of experienced doctors and then turned their diagnostic knowledge into a huge set of rules that the system could use to make diagnoses.
So you would interact with MYCIN by answering questions. And based on your answers and the rules it had, it would try to figure out what was wrong with you.
Exactly. It was like having a virtual doctor. And another interesting development during that time was the rise of logic programming with languages like Prolog. The idea was to express knowledge in a logical form and then let the computer use its built-in reasoning abilities to solve problems.
And our expert source mentions an example of a war planning system built using Prolog, right?
Yeah. David Warren developed a system that could solve complex planning problems in a simulated environment called the blocks world, using a remarkably small amount of code compared to what would have been required with more conventional programming languages.
And this was all thanks to the elegance of logic programming, right?
Yeah.
If you can accurately represent the key facts and relationships of a problem in logical statements, then in theory, the computer can automatically deduce the solution.
It's a very powerful idea, and it has a lot of appeal. But in practice, logic programming also ran into some limitations. It turned out to be inefficient for certain types of problems, and it wasn't very well suited for tasks that involved interacting with the real world, like robotics.
Right. And as our expert source mentions, trying to manually encode all the knowledge that a modern LLM possesses in a logical, rule-based system would be virtually impossible.
Exactly. But speaking of ambitious attempts to encode knowledge, there's the story of Project Psych, which started in the 1980s.
Ah, yes, the quest to build a machine with all of human common sense. Tell us about that one.
Well, Doug Lenat, the visionary behind Psych, was convinced that the key to achieving true artificial intelligence was to give machines a vast amount of knowledge about the world. So he started this incredibly ambitious project to manually encode common sense knowledge as a huge network of rules and concepts. It was a massive undertaking. I mean, think about all the things that we humans take for granted, like water is wet, things fall down when you drop them, people get upset when you insult them. Psych was trying to capture all of that explicitly.
And Lennox was really optimistic about Psych, wasn't he? He predicted that it would eventually be able to generate its own knowledge and learn on its own.
Yeah, he thought it would reach a point where it could bootstrap itself into a kind of superintelligence. But unfortunately, Psych didn't quite live up to those expectations. While it did make some contributions to knowledge representation and influence things like knowledge graphs used by search engines today, it was largely seen as a failure in terms of its AI goals. It was just too ambitious, too hard to scale up. And it became a bit of a cautionary tale about the dangers of AI hype.
There's even that funny quote in the source, defining a microlenot as a unit of bogusness. It's kind of a harsh reminder of how things can go wrong when expectations get too high.
Yeah, it's a good reminder that with each new wave of AI excitement, there's always the risk of overpromising and underdelivering. And it's interesting to contrast Sykes' approach of manually encoding knowledge with the way modern LLMs learn. These models are trained on massive amounts of data, and they kind of discover patterns and relationships on their own without needing humans to explicitly tell them what those patterns are.
Right, so it's a move away from handcrafted knowledge to data-driven learning. And that shift is really important for understanding the success of modern AI. But before we dive into that, let's talk about another interesting detour in the history of AI, behavioral AI.
Ah, yes. Behavioral AI emerged in the late 1980s, early 1990s, as a sort of rebellion against the dominant symbolic AI paradigm. Rodney Brooks, who was a leading figure in this movement, argued that the focus on symbolic representations and abstract reasoning was misguided. He thought that intelligence should be grounded in the real world and the ability to interact with the environment and to behave in ways that are appropriate to the situation.
So instead of trying to build a machine that thinks like a human, they were trying to build a machine that acts like a human.
Yeah, or at least acts in a way that's intelligent. Brooks's approach was called behavioral theory, and it was based on the idea that intelligence emerges from the interaction of many simple behaviors. Think of it like a bunch of reflexes that are triggered by sensory input.
So rather than having this central symbolic representation of the world and planning out every action in advance, the robot would just react to its surroundings based on these pre-programmed behaviors.
Exactly, and Brooks actually had a lot of success with this approach. He built robots that could navigate complex environments, avoid obstacles, even do things like collect soda cans. These robots were much more robust and adaptable than the earlier, more deliberative robots that were based on symbolic AI.
But didn't behavioral AI also run into some limitations?
Yeah, it did. One issue was that as the complexity of the robot's tasks increased, the number of behaviors you had to program also exploded, and it became very difficult to manage and coordinate all these different behaviors. It was another kind of combinatorial explosion, but this time at the level of behavior rather than search. But even though behavioral AI didn't solve all the problems, it did have a lasting impact on robotics. The Roomba vacuum cleaner, for example, is a very successful commercial product that's based on some of the principles of behavioral AI.
Right. So it's a good example of how even approaches that don't fully pan out can still lead to practical applications. And it's another reminder that the history of AI is full of twists and turns, with different ideas coming in and out of favor. Now, let's move on to another paradigm that emerged in the early 1990s, agent-based AI. What was that all about?
Agent-based AI was an attempt to kind of synthesize some of the best ideas from earlier approaches. It wanted to combine the proactive, goal-oriented aspects of symbolic AI with the reactive, real-world grounding of behavioral AI. And it also introduced the idea of social interaction between multiple intelligent agents.
So instead of just having one AI system that you interact with, you'd have multiple AI systems that could communicate and cooperate with each other.
Exactly. The vision was that we would have these software agents that could act on our behalf, doing things like scheduling appointments, managing our finances, or even negotiating with other agents on our behalf. Think of it like having a personal assistant, but one that's actually intelligent and can learn and adapt.
And this idea of agents is still very relevant today, isn't it? I mean, we have Siri, Alexa, Cortana. These are all examples of digital assistants that are based on some of the principles of agent-based AI.
Yeah, exactly. And those systems are really just the tip of the iceberg. Researchers are exploring all sorts of possibilities with multi-agent systems, from coordinating swarms of robots to managing complex supply chains to creating more realistic virtual characters in games and simulations. And it's interesting that agent-based AI is not tied to any specific underlying technology. You can implement agents using symbolic AI techniques or connectionist approaches like neural networks.
Which brings us to a really interesting question.
Mm.
What does the agent-based perspective offer to the current landscape of AI, which is dominated by these massive language models?
That's a very active area of research right now. People are trying to figure out how to integrate these incredibly powerful language models into an agent-based architecture. Can you create an AI agent that not only understands and generates language, but also uses that language to reason about the world, to plan actions, to interact with other agents in a meaningful way. It's a very exciting area, and it has the potential to really push the boundaries of what AI can do.
Right. And speaking of pushing boundaries, Professor Wooldridge himself has been a big proponent of agent-based AI throughout his career. In fact, our expert source mentions that he kind of had this aha moment back in the 1980s when he realized that the future of computing was going to be all about interconnected networks, and that this would open up all sorts of possibilities for networked AI systems.
Yeah, he was really ahead of his time in that sense. And while he didn't predict the specifics of the internet as we know it today, he did foresee this trend towards greater interconnectedness and distributed systems, and he believed that AI would play a key role in that future.
It's fascinating to think that his initial vision wasn't a centralized search engine, but a decentralized network of intelligent agents interacting directly with each other.
Yeah.
And it seems like we're moving in that direction, even if it's happening in ways that he might not have anticipated.
Exactly. I mean, think about the Internet of Things, IoT, with all these devices being connected and sharing data, or the rise of decentralized platforms like blockchain. These are all trends that point towards a future where AI systems will need to be able to communicate and cooperate with each other in a much more sophisticated way than they do today.
Okay, so we've covered a lot of ground here, from Turing and the golden age of symbolic AI to the rise of expert systems, behavioral AI, and agent-based AI. It's clear that AI has had a very rich and interesting history, with a lot of different ideas being explored and debated along the way. But now let's shift gears and talk about the approach that has really taken center stage in recent years: connectionism, or the attempt to model intelligence by mimicking the structure and function of the human brain.
Right, and this is where machine learning and specifically neural networks comes in. This approach actually has its own long history, going all the way back to the 1940s. There were early attempts to build artificial neurons and to connect them together in networks that could learn, but the technology wasn't quite there yet. It wasn't until the 1980s that we saw the emergence of algorithms like backpropagation, which made it possible to train deeper and more complex neural networks.
And then in the 2000s, with the increasing availability of data and computing power, we saw the rise of deep learning, which really revolutionized the field.
Exactly. And now we're in the era of transformers and these massive foundation models, which are capable of doing things that were previously thought to be impossible.
Oh.
It's pretty ironic when you think about it. The approaches that initially seemed so promising, those attempts to explicitly program intelligence through symbols and rules, have been largely overshadowed by this approach that basically tries to mimic the brain, even if we still don't fully understand how the brain works.
Right. And the success of these neural network-based approaches is largely due to the fact that we can now train them on massive data sets using incredibly powerful computers. It's another example of how technological advances can drive scientific progress. But it also raises some interesting questions about the nature of intelligence itself.
One of the things that Professor Wooldridge highlights in the source material is that these modern AI systems, these foundation models, are fundamentally disembodied. They don't have a physical body. They don't interact with the world in the same way that humans do.
So they're great at tasks that involve manipulating symbols and abstract knowledge, but they struggle with tasks that require physical interaction and common sense.
Exactly. I mean, think about it. We have language models that can write poetry and code, but we still don't have robots that can reliably do basic things like fold laundry or make a sandwich. There's a huge disconnect there.
And in his Turing lecture, Wooldridge makes this distinction between embodied capacities, which AI is still very bad at, and intellectual capacities, where AI has made much more progress.
Right. But what's really interesting is that Wooldridge also argues that even in some areas that we consider to be highly intellectual, like logical reasoning and planning, current AI systems might not be as capable as they seem.
So he's saying that even though these models can do amazing things, they might not actually be reasoning in the same way that humans do.
Yeah, that's his point. He thinks that a lot of what these models are doing is just very sophisticated pattern recognition. They're not necessarily understanding the underlying logic or the causal relationships in the way that humans do.
And he gives some pretty convincing examples, right? Like, if you present a planning problem using unfamiliar vocabulary, even if the logic of the problem is the same, these models often struggle.
Exactly. And that suggests that they're relying more on recognizing patterns in the data they've been trained on than on truly understanding the problem. It's kind of like
Yeah.
they're playing a game, but they don't know the rules. They're just really good at guessing what move to make based on what they've seen before.
That's a really interesting perspective. So while these models are undeniably impressive, we need to be careful about attributing too much human-like intelligence to them.
Absolutely. And what's also interesting is that a lot of the questions that were once purely philosophical are now starting to become empirical questions. People are actually doing experiments to try to figure out if these models have any kind of consciousness or if they can genuinely understand and reason about the world.
Yeah, and our expert source brings up this idea that maybe the success of these brain-inspired models actually tells us something about human intelligence.
Hmm.
Maybe we're not as logical and rational as we think we are. Maybe a lot of what we do is also just pattern recognition, but we're just not aware of it.
That's a very provocative idea, but Wooldridge pushes back on that a bit, arguing that humans are fundamentally different from these AI systems because we're embodied and we're constantly interacting with the world. Our intelligence is shaped by our physical and social experiences in a way that these models just haven't been able to replicate yet.
Right. And he acknowledges the emergence argument, the idea that we don't really know how complex phenomena like intelligence arise from simpler components, whether in the brain or in a neural network. But he also points out that the current AI is still largely an engineering hack. It works really well, but it's not based on a deep understanding of how intelligence actually works.
And that raises the question of where AI research should go from here. Should we be focusing more on biomimicry, trying to understand the brain better so we can build more brain-like AI? Or should we continue to focus on these more engineering-driven approaches, even if they don't necessarily reflect how the brain works?
It's a really interesting debate, and there's also this idea, which is often called the bitter lesson, that suggests that most of the progress in AI has actually come from just scaling things up, bigger models, more data, more computing power, rather than from any fundamental breakthroughs in our understanding of intelligence.
Yeah, it's a bit humbling when you think about it, but there's still something kind of magical about what these systems can do, even if we don't fully understand how they do it.
And it's pretty amazing that questions that were once purely philosophical are now becoming testable scientific questions. That's a really exciting development, and it suggests that we're just at the beginning of a very long and fascinating journey with AI.
So, to wrap up our deep dive into the history of AI, we've seen how the field has gone through these cycles of hype and disappointment, with different approaches coming in and out of favor. We've seen the rise and fall of symbolic AI, the emergence of connectionism, and the fascinating detours through behavioral AI and agent based AI.
And now we're in this era of incredibly powerful but disembodied foundation models, and we're still trying to figure out what they can do, what their limitations are, and what their implications might be for the future of humanity.
Understanding this history is crucial for anyone who wants to make sense of the current state of AI and to anticipate where it might be going next. And it's also a reminder that the future of AI is not predetermined. It's up to us as humans to decide how we want to develop and use these technologies.
So here's a final thought for our listeners. Given what we've learned about the history of AI and limitations of current approaches, what do you think needs to happen next? What are the key challenges that we need to overcome to create truly intelligent machines?
And what are the ethical and societal implications of these powerful new technologies? We encourage you to continue exploring these questions, to think critically about the future of AI, and to engage in the important conversations that are happening around this topic.
Thanks for joining us for another deep dive.
Until next time.